that the same thing as the voltage drops you meant? Or
yeah.
Is that also okay?
Because, sorry, I forgot to write equal 0 here, I suppose, right? Because if I look at this, I can break it down into integral of 1 EPL plus integral of 2 EPL, and so on, right? Integral of n EPL, and each of these p's is a voltage drop.
Okay.
Right? Okay. And the sum of all this voltage drop is equal to a closed loop line integral of EPL, because each separate piece is a voltage drop.
The thing that confuses me is, aren't there cases where the integral of EDL isn't 0?
It's always 0 for electrostatic.
Oh. Okay.
Unless you have magnetism, then it's not 0. Right? But if you just dealing with electrostatic, this is enshrined in well, not exactly in Maxwell equation, because Maxwell equation has a magnetic component. But in electrostatic, this is always true.
Okay.
Right? This is just a consequence of Coulomb's law. So, two of the standard canonical example is that when you have a two resistor R1, R2, the battery, right? Then just as an equivalent circuit, this is equivalent to just one resistor, R equivalent. Okay? See, it's confused. No, yeah. But I'm just replacing this with one resistor. Right? And you want to know what is the equivalent resistance. Right? And you know this from your previous study. It's very simple. You just apply, again, there is no branch. You apply the second Kirchhoff law, that you have minus I R1, minus I R2, equals V is equal to 0, so V is equal to I R1 plus R2. Okay, and this is your R equivalent, right? Then V is just I times R equivalent, and R equivalent is just the sum of the two resistance. This is called resistance in series, okay? The other one is resistance in parallel. Find the equivalent resistance here. Just to make it more obvious, I'm going to try it slightly differently. I'm going to try it like this. Okay. So again, here is slightly more complicated. We want to find the equivalent circuit. So in this case, the equivalent circuit is equivalent. Okay. First you have current I here. Here also you have current I. This is V. Here you have to apply both concepts. Concept number one, Kirchhoff law number one, says that I has to be equal to I1 plus I2, right? Okay. Find your own convention, right? As long as you draw it with arrow, then you know what's happening, right? Here I is equal to I1 plus I2, okay? And from the second concept, second Kirchhoff law, right? The reason I call it concept is because I don't want to, it's not nothing new, you already know about this, right? Second concept, I go through two different loops, right? From loop number one, from this loop, again, define it, right? From loop number one, then you have minus I R1 plus V is equal to 0. Right? The potential drop across this is equal to the increasing potential plus the increasing potential across the battery, that's equal to 0. right? I should go through this faster because you're quite familiar with all this. From loop number 2, if I go through the other loop, that loop number 2, then what I have is minus I R2 plus B is equal to 0. Right? So did I make a mistake? Yes. Okay. So here I1 is equal to B over R1, I2 is equal to B over R2, okay? And you substitute this into this equation, right? So, and I'm doing it a bit more pedantically, just following the two concepts. But this will be useful when you analyze a more complicated network. But for simple network like this, you probably can do it slightly better, simply. But at the end of the day, you get the same answer. 1 over R equivalent is equal to 1 over R1 plus 1 over R. Okay. Question so far?
What made you choose the 2 loops? I mean, why loop 1 is that one, and why loop 2? The loops?
Oh, I can choose. I mean, I have 2 unknown. I need 2 equations to solve, right? So for one of the equation, I go to one loop, or three equation, 3 unknown, I suppose. But the first equation.
You mean like this little one here?
Yeah, this one is going through this loop.
Okay, yeah, and then
The other one goes through that.
That's the letter.
Right. The sum of the potential has to be 0 in either loop. Right? That's the reason I have this. Okay. And with this, you have all the machinery to solve a much more complicated network. Okay. I have a few more minutes. If I can introduce this one concept. So here is your resistance, right? It's an ohmic material. So what happened is that if I transport a charge across R, right, then the battery, the demon here, okay? So we never talked about Maxwell demon in thermodynamics, yeah? We forgot to talk about that. But the demon here moved the charge here, is doing work, right? The work that he did here is exactly the work that's performed by the electrostatic system, right? And what happened here, the moving charge from high potential to low potential, right? And then you get something out. In this case here is Q, if this is charge Q, times the potential difference V, right? Okay? And the work that you do in moving this across, right, what happened is that you accelerated this charge across this material, right, and it's bumping around, so it's losing the kinetic energy acquired by dropping down the potential hill here, okay, and it's losing it in the peak, right, so it gets accelerated, and then it's scattered, right, and then they transfer a lot of the kinetic energy into the solution. Right? So this work done will heat the ohmic material. Whatever it is, solution, metal, semiconductor, insulator, whatever material we have here. And power, this is power performed by the battery, like a demon, or battery. Power is just the rate of work done, right? It's dWT, right? So this becomes just dQ dt times the potential, right? But dQ dt, in this case here, is just I, right? So again, you have an equation that you're familiar with from your previous lecture of physics, right? This is also familiar from mechanics, from 7A, right? This becomes just I minus B. and has a unit. The unit of P again is what strength with a T with an S.
1 watt or
1 watt or 2 watt strength with that. Okay, and again, just algebraically, this is the same as V squared over R, because IR is equal to V, or this is also equal to I squared, depending on the problem that you're trying to solve. Okay. I think that's all I have for now. I don't have time for another example. But just to think about this at home. If I have a light bulb like this, like the same light bulb in this computer, and I connect it to a battery. 1, 2, 3. Which one will be the brightest? Think of the thing for Wednesday.